There are nearly 15,000 active and inactive satellites orbiting in low Earth orbit, EELEO, today, and the total number continues to grow exponentially. Most of these high-performance polymer-containing space structures were launched only in the past 5 years. Satellites enable many critical activities on Earth, from GPS navigation and global communication to weather forecasting and military operations. Satellites make the world a smaller place. Their outer space performance demands polymeric compositions that withstand harsh environments, including radiation and atomic oxygen exposure, extreme temperature changes, and reactive particle impacts. All aromatic polyimides, polyarylene ether ketones, Polyarylates, various fluorinated polymers, and their corresponding composites collectively provide this exquisite performance. Furthermore, engineering polymers replace heavier metallic structures to minimize energy consumption, enable precision form factors, and ensure a metal-free, safer demise upon atmospheric re-entry. For example, aromatic polymers convert to carbon at high temperatures. High-performance polymers are driving space innovation. The aerospace industry is evolving at a rapid pace. From reusable spacecraft to ever-smaller, high-performance satellites, the demands placed on materials have never been greater. Traditional metals and composites alone can't always deliver the combination of lightweight strength, durability, and resistance to extreme environments required beyond Earth's atmosphere. This is where advanced polymers step in, providing reliable, high-performance solutions that enable space exploration and satellite technology. The challenge of space. Space presents some of the harshest operating conditions known. Extreme temperatures ranging from -150 degrees Celsius in shadow to +150 degrees Celsius in direct sunlight. Vacuum exposure that causes outgassing and material degradation. Radiation that can alter material properties over time. Weight sensitivity, where every gram matters in reducing launch costs. Lunar dust can cause seal leaks and bearing seizure in critical aerospace mechanisms. Polymers designed for aerospace must perform flawlessly in these conditions while maintaining long service life and ensuring zero risk of contamination. Applications of high-performance polymers in spacecraft and satellites. Thermal insulation and protection. Ethylene Tetrafluoroethylene, ETFE, and Polytetrafluoroethylene, PTFE, films are widely used in satellite insulation blankets. They provide thermal stability, low outgassing, and excellent radiation resistance. Cabling and wire coatings, Perfluoroalkoxy alkane, PFA, and fluorinated ethylene propylene, FEP, coatings protect critical wiring from temperature extremes and abrasion. They ensure reliable data and power transfer across spacecraft systems. Sealing and bearings, PTFE, and engineered fluoropolymer seals maintain integrity in propulsion systems, docking mechanisms, and life support units. They provide low friction and reliable sealing in vacuum conditions. Semiconductor-driven electronics. High-purity fluoropolymers are critical in the manufacture of semiconductor components used in satellite electronics. They resist aggressive chemicals during wafer processing, ensuring the high reliability needed for space applications. Benefits of polymers in aerospace innovation. Lightweight performance. Reduces launch costs and improves payload capacity. Durability. Withstands radiation, vacuum, and mechanical stress. Safety and reliability. Eliminates the risk of outgassing that can damage sensitive instruments. Versatility. Custom formulations can meet specific mission requirements. Enabling the future of aerospace. As the aerospace sector pushes further into reusable spacecraft, satellite constellations, and long-duration missions, the role of advanced polymers will only increase. Whether protecting delicate electronics, enabling propulsion systems, or insulating satellites from the cold void of space, polymeric materials are already shaping the next generation of aerospace and defense innovation. Aromatic polyimide, PI. Aromatic polyimide is a high-performance polymer with imide rings and aromatic groups in its backbone, known for exceptional thermal stability, mechanical strength, chemical resistance, and electrical insulation, making it crucial in aerospace, electronics, flexible circuits, insulators, protective layers, and automotive industries for applications like films, coatings, and composites. They are synthesized from aromatic diamines and dianhydrides, typically via a polyamic acid precursor, and are valued for their durability in extreme conditions. Aromatic polyimides and polyethers offer exceptional thermal, chemical, flame, and radiation resistance for many emerging transportation, electronic, and aerospace applications. Printed aromatic polyimides enable conversion to carbonaceous objects upon pyrolysis, as confirmed with various measurements. Key properties of aromatic polyimide. Thermal stability. Withstands continuous temperatures up to 300 degrees Celsius or higher without significant degradation. Mechanical strength. Offers high stiffness, toughness, and dimensional stability. Electrical insulation. Excellent dielectric properties. Low dielectric constant. Suitable for electronic components. Chemical resistance. Resists a wide range of solvents, acids, and bases. Processability. Can be formed into films, fibers, coatings, and composites. Applications of PI. Electronics, flexible circuit substrates, integrated circuit layers, sensors, high-temp capacitors. Aerospace, wire insulation, structural components, protective coatings. Polyarylene ether ketones. Aromatic ketone polymers, sometimes referred to as polyarylene ether ketone, belong to the class of high-performance engineering thermoplastics, which contain both ether groups and ketone groups in the polymer backbone. Commercialized PAEKs are mostly semi-crystalline polymers. Many polyarylene ether ketones, PAEKs, are high-performance engineering thermoplastics with outstanding properties. The semi-crystalline members are tough materials that show excellent thermooxidative, hydrolytic, and solvent resistance. The crystalline nature of these polymers contributes to their toughness and stems from similar bond angles of the aryl ether and ketone linkages. The presence of para-arylene linkages in the polymer chains causes these polymers to crystallize from the melt. Drawbacks include high cost and high melt processing temperature. In some cases, the glass transition temperature is relatively low, compared to that of polyarylene ether sulfone and polyarylene ether imides. Polyarylates. Polyarylates, PARS, are a family of aromatic polyesters derived from aromatic dicarboxylic acids and bisphenols, characterized by their semicrystalline and amorphous forms, high thermal stability, and applications in the electrical and automotive sectors. They exhibit properties such as dimensional stability and good impact strength, but have poor chemical resistance to certain solvents. Polytetrafluoroethylene, PTFE. PTFE is made up of fluorine and carbon atoms. The fluorine atoms are just the right size to form a helical shield around the carbon atoms. This stops any chemical attack on the carbon atoms because nothing can get close enough. Fluorine is an extremely reactive element, and as a result, the chemical bond between it and carbon, is one of the strongest known in organic chemistry. This is why PTFE can be attacked only under extreme conditions. The forces between polymer chains are extremely small, which gives PTFE its excellent low coefficient of friction. Polytetrafluoroethylene, PTFE, commonly known as Teflon, is a synthetic fluoropolymer composed exclusively of carbon and fluorine atoms, with a chemical formula of. It features a carbon backbone chain, where each carbon atom is bonded to 2 fluorine atoms. This structure creates an extremely strong, stable, and chemically inert material. Key details about PTFE structure and properties. Composition: PTFE is a fluorocarbon solid, meaning it consists entirely of carbon and fluorine. Structure: it is a linear polymer formed by the polymerization of tetrafluoroethylene, TFE. The carbon-fluorine bonds are among the strongest in organic chemistry. Protection mechanism: the fluorine atoms are sized perfectly to form a helical sheath around the carbon chain, protecting it from chemical attack. Properties: non-stick or low friction. It has one of the lowest coefficients of friction of any solid. High temperature resistance. It remains stable at high temperatures with a melting point of approximately 327 degrees Celsius. Chemical inertness. It is resistant to nearly all chemicals, including acids, bases, and solvents. Common uses: non-stick cookware, industrial seals, wire insulation, and corrosion-resistant coatings. The material was discovered in the late 1930s and is widely used for its unique combination of stability, low friction, and non-stick capabilities. Perfluoroalkoxy alkane, PFA. PFA is a copolymer product of PTFE. The comonomer perfluoroalkyl vinyl ether interferes with the crystallizability and molecular weight to achieve good mechanical properties and melt processability without sacrificing thermal performance and chemical resistance. The key advantage of PFA is its melt processability because of lower melt viscosity than PTFE. Because of the high strength between carbon, fluorine, and oxygen atoms, PFA exhibits similar properties to PTFE over a large range of temperatures. Some other differences from PTFE are good permeability resistance because of lower void content and better deformation, cold flow resistance. Perfluoroalkoxy alkane, PFA, is a melt-processable copolymer of tetrafluoroethylene, TFE, and perfluoroalkyl vinyl ethers, often described as a modified meltable form of PTFE. It combines the chemical resistance and high-temperature performance, up to 260 degrees Celsius, of PTFE with the ability to be processed via conventional injection molding and extrusion. Key aspects of PFA as a copolymer. Composition: PFA incorporates side chains, perfluoroalkoxy groups, that reduce crystallinity, allowing it to melt and flow, unlike PTFE. Properties: it retains extreme chemical inertness, low friction, and high purity, similar to PTFE. Advantages over PTFE: PFA offers superior transparency, higher flex life, and improved resistance to stress cracking. Applications: widely used in semiconductor manufacturing, chemical handling, tubing, and medical components. Ethylene Tetrafluoroethylene, ETFE. ETFE is a fluorine-based plastic and could be described as a tough, high-strength version of PTFE. It has excellent chemical, electrical, and high-energy radiation resistance and a relatively high melting temperature. Properties such as chemical inertness, outstanding weathering and heat resistance, excellent electrical insulation, and low coefficient of friction enable ETFE to be exploited in a diverse range of applications such as football stadium roofing, wire insulation, insulated transformers, and surface coatings. ETFE is less flexible than PTFE but has far superior abrasion resistance. Ethylene Tetrafluoroethylene, ETFE, is a high-strength, fluorine-based thermoplastic copolymer, polyethylene tetrafluoroethylene, known for exceptional corrosion resistance, durability, and high light transmittance. Often used as a lightweight alternative to glass, it is frequently employed in architectural, aerospace, and solar applications due to its self-cleaning properties and wide temperature tolerance. Key characteristics and applications. Material properties. ETFE is a durable and lightweight material with excellent chemical, radiation, and electrical insulation properties. It is more resistant to abrasion and tougher than PTFE. Architectural use, frequently used in stadium roofs, for example, Allianz Arena, and building facades for its ability to transmit UV light, self-cleaning abilities, and lightweight. Industrial applications, used for wire coatings in the aerospace industry, nuclear industry cable wraps, and chemical tank linings due to its high-performance properties.